Swayam Prabha. Digital India. Educated India.
So there's a voting rule that's based on the pairwise majority graph that's even simpler than the Boda count, in the sense that we don't even worry so much about the margins. So I'm going to define for you the Copeland score of a candidate, but before I do that, I don't know, maybe I want to ask you if there is, so if I just give you the pairwise majority graph, okay, which is this object that we saw here without the margins. So I mean, I can build this graph based on the election, and let's say we lost the election to some computer crash, the election data is gone, but you somehow have the graph. So you don't have the data on the margins, but you just have the graph. So apart from talking about the Condorcet winner, which has the problem that it may not exist, what is another natural way of defining a winner based on this pairwise majority graph? So you have information about who won the pairwise contests, right? What would you try and parse out of this? So if you focus your attention on, so maybe let me just draw an abstract tournament. I'm just making this up on the fly, sorry. So here maybe we have a majority cycle. So there is no Condorcet winner because here you have a majority cycle and the other candidate is getting defeated at least once. So if you focus your attention on a particular candidate, what is it, how would you like to summarize the performance of this candidate in this election? So this candidate here right on top, right, it loses one and wins two. That's the kind of information that you want to perhaps add to your summary. So it lost one. Sorry, yeah, it lost to D and it won against B and C, right? So oh, sorry. Okay, so so the convention is that the arrow is from A to B if A is winning. So sorry. So so A wins against B, wins against C, and loses to D. Is that a fair summary? Okay, so my convention is that I put an arrow from X to Y if X wins. So have I flipped the convention? Sorry. So here, for instance, okay, but let me just make sure that here at least it's consistent. So here we have said that this is an arrow going from B to A, and indeed, okay, so I think I have flipped my convention, sorry, in both cases. So at least it was consistent so far. All right, so maybe let me try to keep it consistent at least within this discussion, but I'm afraid I may have spoiled your habit because it's, I think at least in the book I believe it's the other way. So in any case, let's do this what's important is that I want to get the counts in. So here A is losing 2 and winning 1. Yeah? Okay, so the incoming arrow indicates a win. So B is winning 2, D is winning 1, C is winning 2. And this is the remaining. Okay. So this is sort of the situation. So these wins and losses, can you convert them? Can you convert this information into some sort of a score and come up with a voting rule based on that? Okay, so wins minus losses, right? So for every candidate, count the number of candidates that she is beating versus the number of candidates against whom she is losing, and that difference is the Copeland score of the candidate. So is Copeland a Condorcet consistent rule? I mean, the rule is just this: you look at the majority graph and you do this wins minus losses information, and then you choose the candidate that has the highest Copeland score. As you can see, Copeland also may lead you to ties. Here, for instance, B and C share the same Copeland score. So you may have multiple candidates with the same Copeland score. That's already a bit of an issue. Also, note that here every edge in this graph is actually a win or a loss. Although if your election consists of an even number of voters, it's conceivable that two candidates end up in a draw, right? We haven't looked at that, but you could have edges which are undirected, signifying that there is a draw. So those are situations that we are not accounting for here, but you could easily adapt the Copeland score to account for draws. So wins minus losses already implicitly accounts for draws by saying that we will not count them, okay? But there's also the asymmetric Copeland score which only counts the wins, for instance. And again, it's an easy exercise to check that all of these variations of Copeland will eventually output the same winner, because it's essentially off by the, I mean, they're all kind of related linearly in a fashion that doesn't change the relative ordering of the candidates. So we might as well just focus on the wins minus losses formula for Copeland. And the question was, is Copeland Condorcet consistent? Does the Copeland winner, if a Condorcet winner exists, does Copeland pick it? Yes. What is the Copeland score of a Condorcet winner? The number of candidates minus 1, right? Because a Condorcet winner, remember, beats everybody in pairwise elections. So the number of losses is 0 and wins is every remaining candidate is a win. So that is m minus 1. And that is the maximum possible Copeland score that anyone can have. If somebody has a Copeland score of m minus 1, then every other candidate has a Copeland score of less than m minus 1. Is that clear? Because if you have one person who beats everyone, then everyone has lost at least one of their pairwise contests. So they cannot have the maximum possible Copeland score. So if a Condorcet winner exists, she will also be the unique Copeland winner. But in the event that a Condorcet winner does not exist, so for instance here, I mean, we do have a majority cycle and it is rated differently by Copeland and so on. So there is, so Copeland can do interesting things when Condorcet winners don't exist. Okay, so I promised you that I will allude to the issue of cheating along the same lines that you have seen in the context of matching. So let's just talk about this a bit. So again, I'll outline an example for you. It's okay, so while I'm writing this down, one quick question. So in plurality, so by manipulation, let's just, so again, there are probably multiple ways of cheating in an election. But for now, let's just say that a voter changes their ballot to suit themselves. Okay, so I have a truthful preference, which is my true ordering of the alternatives. But can I get the system or the mechanism to output a better alternative by submitting a fake preference? Okay, so by changing, so it's very similar to what we were doing when we were cheating with regards to matching. So we submit a fake alternative, fake preference over the alternatives and try to persuade the mechanism into giving us something that is better. So is it possible to manipulate plurality, for instance? So in plurality, remember that the mechanism does not even account for information that is beyond the top position. So what is the best that you can hope to do in plurality? So just intuitively, does it make sense to, so let's say that the plurality winner, so in some abstract election, the plurality winner is A, and A is not, sorry, so A is not your favorite candidate. That's why you're even thinking of manipulating. If A was your top option, you wouldn't even bother, right? So if A was not your top candidate and somebody else was, so let's say your preference was B over C over A, and clearly A is not winning, what can you do? I mean, for example, so you cannot make B win by changing your preference. Is that clear? If you change your preference, if anything, you reduce B's plurality score, right? So you cannot make your favorite candidate win by changing your preference. So at best, what can you hope for? Yeah, so maybe you can make C win, which would still be something because you prefer C over A. So again, in plurality, there is only one manipulation strategy that makes sense, which is what? Yeah, just place C on the top because anything else that you do will not change C's plurality score. But by placing C on the top, can you, for example, decrease A's plurality score? A's plurality score does not change because of your manipulating your vote, right? So A has the same plurality score. So the best that you can hope to do is to increase C's plurality score by 1, which means that if you were in this precarious situation that A's plurality score is maybe, you know, maybe it's a very closely fought contest with C and A's plurality score is exactly 1 more than C's plurality score, then with your manipulation, what you can do is you can bring C to a point where it ties with A, right? And then you kind of hope that there is a tie-breaking mechanism that favors C, but you cannot guarantee or you cannot make C the unique plurality winner by manipulating your vote alone. Okay, so single voter manipulation is pretty limited in the context of plurality, but okay, so you could get your favorite, not your favorite candidate, but you could get a better candidate to tie with the current winner, or you could try to convince some of your friends to manipulate along with you, and then probably you can actually change the situation quite a bit. Okay. So that is called coalitional manipulation, but for now let me just continue to focus on single voter manipulation. So so here, let me just write down. So for this election, what I wanted to do was work out the Copeland scores. So I have the majority graph, but in the interest of time, let me just write down the Copeland scores directly. So B has a Copeland score of -2 and E has a Copeland score of +2 and everyone else has a Copeland score of 0. Okay. So what I'm asking is Copeland vulnerable to this kind of manipulative behavior? So is it possible for somebody to misrepresent their vote and actually get a better outcome. So maybe let me actually draw the majority graph here. So AC and D all have a Copeland score of 0, which is to say that they win 2 and they lose 2 of their pairwise elections. B has a Copeland score of -2 and E has a Copeland score of +2. This is because if you look at E, so the notation here is that between A and B, A wins over B. Okay, so 4 voters prefer A to B and 3 voters prefer E to A. B to A, sorry. So between A and C, 2 voters prefer A over C and the remaining 5 voters prefer C over A. Okay, so that's the notation here. So if you look at E, E is winning against A, E is winning against B and against C, and it's losing to D. So it has essentially a Copeland score of 3 minus 1. So remember that Copeland is wins minus losses, right? So E wins 3 of its pairwise elections and loses 1. And if you look at the last 2 voters whose vote is A, B, C, D, E, for them this is a bad situation. Why? Yeah, E is their least preferred candidate and E is winning the election, right? So is it possible for one of these voters to change their vote and affect the outcome of the election for the better? Any different outcome will be good for them because he is their least preferred candidate. So even if you can get D to win, that will be better than the current situation. So is it possible to influence the outcome of this election by changing one of the last 2 votes, for instance? Okay, so I'm going to request that we focus on single voter manipulation, meaning that maybe one of these voters comes away to change their vote. Okay, so we'll come back to both of them colluding to manipulate. That'll clearly that'll have a greater impact because you have more leeway to do things. But what if one of them decided to submit a false preference? How much damage can they do in terms of changing the outcome of the election? So let's just think about if we can make D win, because I've looked at the example before you have, so I know that that's something that is possible to do. So let's look at the scores for D. So D is losing to A and D is losing to C, but is winning against B and winning against D. Okay, and notice that the wins against B and E are with a decent margin, meaning it is 5-2, right? So D has 5 voters preferring it over, meaning that there is some leeway. Even if D loses one of its votes the other way, even then D will continue to dominate these two pairwise contests because there is some margin. On the other hand, where D is losing to A and C, these are closely fought elections. This is 4,3, which means A has 4 voters preferring it over D, and there are 3 voters who prefer D over A. So a switch here would actually make D fare much better. So, and notice that if only one voter is manipulating, what is their extent of influence on these pairwise elections? Can they make it, like, can they make a, I don't know, yeah, so you cannot make a 20-20 go to, 15-25 by just changing your vote. Your vote is just going to have the influence of at most one flip. Either your pairwise preference stays the same, in which case that contest is not affected at all, or it goes from being like this to, you shave off one from here and you increase this by 1. That's the extent of influence that you can have by changing one vote. So if an election is not closely contested, you are not going to actually change the outcome. So in fact, the good outcomes for B and D, you are not going to run the risk of destroying them because the margin there is a lot of cushioning. So you don't run the risk of making it worse for D. But on the other hand, you have the scope for improving the closely contested elections with A and C. So how do you think you can change this vote to actually execute this plan? Right, let's just keep D in the first place. And I guess it doesn't even matter what you do to the rest. So if you keep D in the first place, the fate here is going to flip. So previously what was happening was that D was losing to D was losing to A, B and C in the original vote, right? Because you placed D fourth. So D was losing to A, B and C. So as far as A and C in particular are concerned, because of this flip, these fates are going to change. So this 4,3 will become now 3,4, right? So because A has lost one of its supporters relative to D, and similarly C has also lost one of its supporters relative to D. So the 4,3 again for CD also becomes 3,4. The other two elections only improve or stay the same by putting D on top. Okay, so this is one way in which you can in fact improve the score of D, the Copeland score of D from 0 to okay, so are you ending up with a tie? Do we have, so 3 plus 2, 5, so we have 7 voters, right? So you should not have a tie. So will you end up with a tie anywhere? So with B and D, between B and D it will become 3,4, right? And D is still winning. And between D and E again it will be the same 5,2 because D was anyway doing better, right? So the Copeland score is in fact 4 because now D is winning all the pairwise contests, right? Which in fact upgrades D to the level of not only a Copeland winner but even a Condorcet winner, because there are now 4 alternatives and D is beating all of them. And you can check that this is one way of manipulating. Even if you flip the order, you will achieve the same effect. So if instead of A, B, C, D, E, you submit E, D, C, B, A, that will work as well, because as I said, there E is doing better than D, but this election has enough cushioning, so it will not affect that election. And there are probably other ways that you can manipulate as well. So there are in fact multiple ways that this voter can change her preference to improve the outcome of the election with respect to their true preferences, right? So D was preferred over E in the true preference, and so you could subject Copeland to this kind of, to this kind of manipulative attack. So this is just to say that voting mechanisms can be vulnerable to cheating. It is possible, which leads to two natural questions, and one is, can you design a voting mechanism which is robust to this kind of cheating? Can it be built into the mechanism itself? Can the mechanism be cognizant that voters may be unscrupulous, and therefore we should design the rule to kind of circumvent it? And to some extent plurality is like that, but it does that at a very large cost. And it also does not necessarily protect you from coalitional manipulation where multiple voters may collude. And the other issue is, from the point of view of the manipulator, we had an ad hoc procedure to discover that you can manipulate. But given an election instance and given that you want to manipulate, how do you figure out a manipulating strategy? That's the same question that you addressed for matchings as well. And that's the same question that comes up here. And of course, the manipulation strategy will have to, the answer to that question will be closely tied to the mechanism that is in place. So it turns out that some mechanisms are easier to manipulate from a computational perspective, meaning that you can come up with efficient algorithms for figuring out a manipulation strategy, whereas there are other mechanisms which turn out to be a little harder or less obvious to manipulate algorithmically. So, so essentially these two questions lead to two different perspectives on the problem. The first question, where we said, can the mechanism itself be robust to manipulation? Can we build it into the mechanism so that voters naturally have no incentive to cheat? That is what one might call an axiomatic perspective. You are saying that this is a desirable property of a voting mechanism, that it should not be vulnerable to manipulative attack. And can we come up with a voting rule that has this desirable property, among others? So the axiomatic perspective basically says that here are a bunch of properties that we would like our mechanisms to exhibit. So for instance, suppose the mechanism is spewing out a ranking rather than a winner, right? So we said that we may want to output a ranking which reflects the societal consensus. Then you might want to say things like, if every one of you prefer A over B, then in the output ranking also we should rank A above B. It doesn't make sense to not respect a unanimous decision, right? So if everyone likes A over B, then the output should also like A over B. So that's an example of a desirable property, and there are many such natural properties that you could come up with that you say that a voting mechanism should respect. And non-vulnerability, meaning not being vulnerable to manipulative attacks, is one such property. And the question therein becomes, well, can you satisfy a few natural properties together along with non-manipulability? So that's one sort of question which unfortunately turns out to have a somewhat negative answer, and we will try to formalize this more in due course. But the other question, which takes a slightly computational point of view, where you say, okay, I mean, maybe the mechanism itself cannot be hardwired to avoid manipulation, but perhaps we can discover that it is not easy for a manipulator to find a manipulative strategy, right? Maybe it is computationally challenging, in which case it is as good as practically infeasible. So that is a line of thought that has been scattered across several recent papers, but that's a line of thought that's also been severely debated, because you could theoretically establish the hardness, the computational hardness of manipulation, but it's still possible that you can try some ad hoc strategies like we've been doing, and that heuristics work well in practice. So, so it's a very interesting debate, and it applies not only to the manipulation problem the way that I've stated it, but it also applies to other forms of doing undesirable things like control, which we alluded to in the beginning, control by deleting voters, deleting candidates, and other forms of control. So these are all interesting strategic issues that come up, and we will be focusing a little more on the computational view as opposed to the axiomatic view, but we will at least state the theorems that are known in the axiomatic world which motivate the computational investigation. So that is sort of the plan for much of what we will do tomorrow.